You know, I mean, basically a century now, our relationship with vehicle energy has been completely static.
Oh, yeah, totally.
Like gas stations are basically just fire hydrants, right?
Right.
They are these massive pieces of physical infrastructure permanently glued to the ground, and when your tank is empty, you have to go to them.
Yeah, you go to the source.
Exactly, it's binary, it's fixed. But you step into the world of electric vehicle infrastructure today, and well, that old stationary paradigm is completely crumbling. We are looking at a landscape that is just incredibly fluid.
It really is. It's the absolute definition of a paradigm shift. I mean, we are moving away from that centralized, location-dependent model, where you have to basically drag your car to the mountain.
Right.
Instead, we are looking at a dynamic living ecosystem where the energy actually routes itself to you.
Which is wild.
It is,
Oh.
because the future of electric vehicles, it isn't just about engineering bigger, heavier batteries to haul around. It's about completely reinventing how and where and when we charge.
Okay, so let's unpack this for a second because we're pulling from three really distinct sources for this deep dive today. We've got two cutting-edge academic papers, one on an AI framework and another on vehicle-to-vehicle charging, plus some industry news about a mobile charging trick. And the mission here is to synthesize all this to show where EV charging is actually going.
Yeah, because the logistics of millions of EVs pulling megawatts of power simultaneously is it's staggering.
It's a nightmare, right? I mean, if everyone plugs in at 6 p.m. after work, the grid doesn't just get stressed. Like, without intervention, transformers would literally blow.
Oh, absolutely. They would melt.
Yeah. So to solve this, we are looking at some incredible software solutions, specifically a framework called KMAC DRA, which powers an AI system called Smart2Charge.
Yeah, Smart 2 Charge. And managing a modern EV grid is an insanely complex mathematical balancing act.
Yeah.
You aren't just sending electricity down a wire anymore.
Yeah.
This Smart 2 Charge framework, it uses deep Q networks and graph neural networks to process like 20 different contextual features simultaneously
Wait,
in real time.
I want to stop you right there because throwing around terms like graph neural networks can sound like pure magic to a lot of people.
Sure, yeah.
How does that actually work in the context of, a city's power grid?
So think of a graph neural network like mapping a giant interconnected spider web.
Okay.
Traditional software might just look at one charging station in isolation and say, okay, this station needs power.
Just looking at the one spot.
Right. But the graph neural network visualizes the entire city grid as nodes and edges, so the intersections and the threads between them.
Oh, I see.
Yeah. So it doesn't just monitor the local station. It watches how plucking a thread in, say, the industrial district, sends vibrations all the way over to a residential suburb.
Wow.
It can predict a power surge or a bottleneck before it ever even happens because it sees the whole web vibrating.
That makes a lot of sense. And the deep Q network part.
So that's the learning engine. It basically uses a system of trial and error running millions of simulations to figure out the absolute best way to route power through that web to keep it perfectly balanced.
Right.
And it's doing this while tracking 20 real-time variables. So we're talking fluctuating grid loads, traffic congestion outside the charging stations, minute-by-minute weather patterns, and even real-time wholesale electricity pricing.
So it's essentially acting as this highly diplomatic air traffic controller that cares equally if you get to work on time and if the local power transformer catches fire.
That is a brilliant way to conceptualize it, actually. It is constantly negotiating. The algorithm actually assigns strict weights to 5 competing stakeholders on the grid.
Okay, who are they?
So EV users get 25% of the priority, the grid operators get 20%, the charging station operators get 20%, commercial fleet operators also get 20%, and then environmental factors like utilizing renewable energy, they get 15%.
Okay, wait, I have to push back on this weighting system for a second. Because on paper that sounds great, but in reality, how does the AI actually balance that environmental 15% against an EV user who just wants a cheap, fast charge right this second?
Right, yeah.
I mean, if I'm trying to get my kid to soccer practice, I really don't care if a local solar farm is operating at peak efficiency,
Yeah.
I just need a charge.
Right, and what's fascinating here is how the system uses what they call dynamic attention mechanisms to prevent exactly that kind of frustrating user experience.
Right.
It's not a rigid, unyielding hierarchy. The attention mechanism allows the AI to actually shift its focus based on the real-time context.
Oh, so it adapts.
Exactly. So let's look at your driveway. If the wind is howling at 2 a.m. and wind turbines are overproducing, the AI's attention shifts to that environmental 15%.
Okay.
It gently nudges the system to use that excess clean power by offering you an incredibly cheap charging rate to top off your car right then and there.
Oh, I see. So it incentivizes me to align with the grid's needs. I get my fast, cheap charge for soccer practice, and the grid gets to offload excess renewable energy without wasting it.
You've got it. And the data backs this up beautifully. The developers validated this model using a massive data set of over 441,000 real-world charging transactions.
Wow, almost 500,000.
Yeah, across 13 stations in China over a 2-year period. And by using this dynamic attention, weather-aware charging increased renewable energy utilization by 18% during favorable conditions.
500,000 real transactions is a serious stress test. So what were the overarching results when they let this AI air traffic controller actually run the show?
The outcomes dramatically outperformed traditional grid management. I mean, the AI achieved a 92% coordination success rate among all those competing stakeholders.
That's huge.
It is. And for the everyday user, that translated to a 10% reduction in charging costs. Yeah. The system also saw a 15% improvement in overall energy efficiency, and perhaps most importantly for the utilities, a 20% decrease in grid strain during peak hours.
Which keeps the transformers from blowing up.
Exactly. And this is the underlying mechanics of why the vehicle-to-grid, or V2G market, is projected to hit $25.5 billion by 2029. Software is transforming the grid from a dumb pipe into a collaborative organism.
A collaborative organism, I like that. But relying entirely on software optimization has a pretty glaring physical limitation, doesn't it? I mean, it is absolutely perfect when cars are connected to a functioning, healthy grid. But what happens when the grid literally cannot reach you?
Right.
Imagine a commercial delivery fleet stranded on a remote stretch of highway or a major construction site that just doesn't have grid access yet. You can't just digitally route electrons to a truck if there's no physical cable to plug into.
No, you can't. The digital ecosystem needs a physical bridge. When the grid stops, you need off-grid, mobile charging infrastructure.
Which naturally brings us to the second source for this deep dive, which is L-Charge.
Yes.
So they have launched a mobile EV charging and roadside assistance truck that operates as this physical intervention, and they have managed to engineer the smallest 60-kilowatt mobile DC fast charger currently on the market.
Which is a big deal, because the footprint of the charger is vital for commercial viability. Because the charging unit itself is so compact, the service truck maintains full use of its bed and storage compartments for standard roadside assistance tools.
Oh, so it's not just a charger on wheels.
No, it makes it a dual-purpose vehicle for fleet operators.
Okay, here's where it gets really interesting, though, and I'm going to play devil's advocate for a second.
Go for it.
This L-Charge truck is built on a heavy-duty Ford 250 to 550 chassis, right?
Yep.
And it is packing a massive 7.3-liter gas engine.
It is.
Isn't it incredibly counterintuitive, or honestly just outright hypocritical, to use a massive internal combustion engine to charge a stranded electric vehicle?
This raises an important question, right, about the actual mechanics of the energy transition. And it requires us to look pretty closely at the engineering.
Okay.
Because the Ford's gas engine doesn't just spin a separate dirty generator in the truck bed. It actually powers the fast charger directly through a power takeoff system, which is commonly called a PTO.
Wait, let me make sure I'm visualizing this correctly, because normally if I wanted to provide 60 kilowatts of fast charging from a truck, I'd have to haul around a massive battery energy storage system, a BAS.
Right, exactly.
And those things weigh thousands of pounds, they take up the whole truck bed, and you have to charge them up before you can rescue anyone.
It's a logistical nightmare, especially regarding commercial weight limits and DOT regulations.
Right. So instead of hauling a giant chemical battery, a PTO means they are mechanically tapping into the Ford's transmission. Like, they're literally stealing rotational energy straight from the truck's drive shaft and converting that mechanical energy directly into electricity.
That is exactly how it works.
Yeah.
Direct mechanical to electrical conversion. Yeah, it entirely eliminates the need for heavy onboard batteries or supplementary fuel tanks. And because it's integrated directly into the truck's powertrain, this setup can actually provide 15 hours of continuous fast charging.
15 hours. That is a staggering amount of power delivery. But, you know, it still burns fuel to spin that drive shaft.
It does, but we have to view this through the lens of pragmatic fleet management.
Huh?
L-Charge designed these PTO systems to run on renewable natural gas, or RNG, and other low-carbon fuels.
Okay, that helped.
And furthermore, the beauty of the PTO is that the charging module only draws power when charging is actively happening.
Oh, so it's not just running constantly.
Exactly.
Well,
Once the stranded EV is talked off, the PTO disengages. This drastically reduces the ambient idling emissions that are notoriously common when you use, separate gas generator solutions strapped to a flatbed.
gotcha. You can really see the advantage when you contrast this with competitors like SparkCharge, who use those massive battery energy storage systems we just talked about. Because batteries are so incredibly heavy and take up so much space, SparkCharge's mobile charging unit actually has to be towed on a trailer by a completely separate vehicle.
Yeah.
If I'm a fleet operator trying to dispatch a truck towing a heavy trailer through dense city traffic just to rescue a dead delivery van, sounds like a massive headache.
It's totally inefficient, both in terms of dispatch time and capital expenditure. So L-Charge's integrated PTO approach, it provides a necessary pragmatic bridge. And the commercial market clearly sees the value in this off-grid bridge too, given that L-Charge recently raised $10 million from Ultra Capital to scale the operation.
Oh, wow, 10 million.
Yeah, they're proving that you can successfully bring the charger to the vehicle rather than forcing the vehicle to limp to a stationary charger.
But, okay, if we follow that logic to its absolute limit, if bringing the power to a parked commercial vehicle is the goal, why stop there?
What do you mean?
Why force the freight truck to pull over and park at all? What if the highway itself or the other vehicles on it became the charger? We are stepping into territory that sounds like pure science fiction, which brings us to our third source.
Yes, we are talking about platoon-based vehicle-to-vehicle charging, or PV2BC.
This sounds exactly like mid-air refueling for military fighter jets, but applied to minivans and commercial freight trucks barreling down the interstate.
The visual of mid-air refueling is highly accurate, actually. Researchers have modeled a system where modular vehicles physically couple together on the move to share electricity.
So they literally connect while driving.
Right. You have an electricity supplier vehicle, the ES, that locks in with an electricity request vehicle, the ER, while both maintain highway speeds. This would completely eliminate stationary charging delays.
To figure out if this jet refueling concept is actually viable for commercial logistics, researchers ran a massive simulation comparing 3 different scenarios.
Yes, they did.
So scenario 1 is our current reality, right? The standard electric vehicle routing problem. Your truck is low on battery, you detour off the interstate, you pull into a stationary charging station, and you sit there losing time and money while you wait.
Right. Then they tested scenario 2, which introduces platooning, but purely for aerodynamic benefits.
Okay.
This is known as the electric vehicle platooning problem, or EVPP. So straight trucks group up in a line to reduce wind resistance and save energy, much like cyclists in a peloton.
Sure.
But crucially, in this scenario, they still rely on stationary chargers when their batteries get low.
And the data on scenario 2 is what really shocked me when I read this. Just platooning for aerodynamics only saved a maximum of 3.65% in total costs.
Yeah, pretty low.
And the reason why is entirely tied to logistics. If one truck has to pull into a rest stop and wait 15 or 20 minutes for another truck to arrive just so they can draft behind each other on the highway, that annoying wait time completely wipes out the financial benefit of the energy they saved.
Right. Time is money.
Exactly. Time is money, and waiting around destroys the ROI.
Which brings us to scenario 3, the PV2VC model. By allowing these vehicles to physically share power while moving, they circumvented the waiting times at rest stops entirely.
Wow.
And the results were dramatic. Charging on the move saved over 11% in energy consumption, it reduced travel time by nearly 12%, and it cut overall operational costs by over 11%.
That is massive. In the commercial freight industry, where margins are razor thin, an 11% operational savings isn't just a minor efficiency bump, it is billions of dollars.
Oh, definitely.
That completely disrupts the logistics market. But the mechanics of actually pulling this off, figuring out exactly how to route these mobile supplier trucks and requester trucks so they meet at the exact right mile marker at the exact right speed without anyone running out of juice.
It's incredibly difficult. The mathematics behind it are exponentially complex. When the researchers tried to map out these moving rendezvous points, they initially used a standard commercial solver, a highly advanced program called MILUP.
Let me guess, it just completely failed.
Spectacularly. I mean, MIL-PL solvers, they're designed for linear problems,
Right.
But here, the variables just explode. You are tracking multiple moving targets. You're constantly calculating their depleting energy levels in real time, mapping divergent trajectories, and trying to find an optimal coupling
Yeah,
point.
all at 60 miles an hour.
Exactly.
Mm.
The MILP solver literally timed out after 2 hours of grinding its computational gears. It couldn't find a solution. The researchers were forced to abandon traditional linear math and build a custom genetic algorithm.
Okay, I know genetic algorithms generally operate on the principle of, like, survival of the fittest, right?
Yeah.
Mutating data to find solutions.
Yes.
So the routing problem was so complex that they essentially had to let the software digitally evolve the perfect meeting points on the highway?
That's the core of it, yeah.
Yeah.
The genetic algorithm generates thousands of possible routing scenarios, some good, some terrible. It then takes the most efficient routes, crossbreeds their data points, and introduces slight mutations. It repeats this evolution over and over, across generations, until it breeds a highly optimized routing strategy that the traditional solver couldn't even comprehend.
That is brilliant. But what happens if the software makes a mistake? Because if you have a massive mobile charger truck driving around the desert rescuing other trucks, you really don't want the rescue truck needing a rescue truck.
Right. And if we connect this to the bigger picture of real-world deployment, the most crucial part of their mathematical model wasn't just the evolutionary routing.
What was it?
It was the strict fail-safes embedded in the code. The algorithm demands that the supplier vehicle always, without exception, retains enough charge to reach the nearest stationary station. It maintains a strict 2 kilowatt-hour safety net at all times.
Oh, so it creates a hard floor that the AI cannot drop below.
Yes, it proves that this sci-fi concept of highway refueling isn't just theoretical daydreaming. It is being rigorously tested against the absolute limits of real-world logistical safety.
So what does this all mean for the listener? We've explored AI algorithms mapping city grids like spider webs, gas-powered trucks mechanically converting their drive shaft energy into fast charges, and fleets sharing power at 60 miles per hour. If you are listening to this right now on your daily commute, how does this reshape your future?
Well, it signals the absolute end of range anxiety.
Yes, because range anxiety, that deep-seated fear of being stranded on the side of the road with a dead battery, it isn't going to be solved just by automakers cramming heavier, more expensive batteries into the floorboards of our cars.
No, it's not sustainable.
Right. It's going to be solved by the rise of charging as a service. The grid is becoming entirely dynamic. In the near future, you will not have to search for a charger. The charger will find you.
Exactly. Whether that means the Smart2Charge AI diplomatically routing your car to a station right as neighborhood solar prices plummet,
Right.
an L-Charge mobile truck rescuing a stranded commercial fleet in a dead zone, or a modular system physically linking with your vehicle on the interstate.
The infrastructure bends to the user, not the other way around.
And that fully dynamic grid leads to a final, slightly mind-bending fact from the Smart2Charge data, something that truly recontextualizes the future of personal vehicle ownership.
Okay, let's hear it.
Throughout this deep dive, we've focused heavily on cost reductions.
Right.
Right. Saving 10% on your bill or cutting fleet costs by 11%.
Right.
But the data reveals something much wilder when this dynamic ecosystem reaches its full potential. When researchers integrated these AI-managed grids with 100-kilowatt photovoltaic solar installations, they didn't just reduce the charging cost to zero.
Wait, what did they do?
Because the AI was perfectly arbitraging the power, buying when it was cheap and discharging when the grid was desperate, they achieved a net present cost of negative $122,962
What?
and a cost of energy of negative $0.043 per kilowatt hour.
Wait, negative, as in the energy flow inverted and they were literally being paid to charge.
Precisely. The future of electric vehicles isn't just about finding a plug. It is about the entire grid becoming so seamlessly optimized, balancing the weather, the traffic, and all those competing stakeholders that the cost of energy literally inverts.
That completely flips the script on what a car is.
It does. We have to stop thinking of our vehicles as depreciating consumer goods that constantly drain our wallets. In a fully optimized, AI-driven grid, your vehicle transforms into a highly responsive, profit-generating asset for the energy network.
So going back to where we started with that century-old paradigm, we are finally unbolting the fire hydrant from the ground.
We are.
We aren't just creating a mobile water source. We are building an intelligent, hyper-connected ecosystem where the water flows exactly to where you are, precisely when you need it most. And if the system works the way this research suggests, you might just get paid for taking a drink. Something to think about the next time you drive past a gas station.